In this video, we're going to look at how we can use properties of confidence intervals for population proportions to help us determine the sample size we need to use when going out to even gather a sample. So this is actually saying I haven't even gone out into my population to take a sample. Let's say I'm interested in the proportion of the population that's in favor of some measure that's on the ballot. I want to figure out what sample size should I use so that my total width of a 95% confidence interval for the population proportion is no more than 1%. All right, so let's think of what we've used so far, what we've learned so far to help us with this. So a 95% confidence interval for a population proportion we found is the sample proportion, like we have in the picture, plus or minus 2 times the standard error of the sample proportion, which means that the width of this interval is 4 times the standard error, because it's twice that. So really this question is saying, okay, I want the width to be no more than 0.01. So let's set that up. And basically, I'm going to put a less than or equal to sign here where I'm saying the width needs to be at most 4 times the standard error. To make our life a little bit easier, I'm just going to use shorthand. I'm going to call this the sigma sub pop. And this is going to be square root of n down here, just for ease of our calculation. So let's start out, because really I'm trying to solve for n. Let's move some stuff around here. And a reminder is that this is equal to the square root of p times 1 minus p, with the sad note that we don't know p. P is the population proportion that we're actually trying to estimate. So we'll come back to that in a minute. Multiply both sides right now by square root of n. I'm going to do that. That's going to give me 4. Okay. And then I'm going to divide both sides by 0.01. So then I can square both sides. These are both positive terms, so this is going to leave the inequality as it stands here. And now I basically need to figure out what to put in for this standard deviation of the population. In the past, we've estimated this by actually using our sample to estimate this population proportion, but I haven't even taken the sample yet. So this is where I'm even in more of a stuck situation. But this is where I can use the actual graph and my knowledge about the standard deviation to my advantage. Because if we look here, p can only go between 0 and 1, which means the square root of p times 1 minus p, well, the biggest it'll ever be is when p is 0.5. And at that point, when p is 0.5, this quantity will be the square root of 0.5 times 0.5, which gets me back to just 0.5. So worst case scenario, this term is at most 0.5. And that's what we're actually going to use here to help us figure out the sample size we should use, because we don't know what our standard deviation is, but the worst case, the standard deviation is 0.5. This is at most. So I'm saying that's the reasoning. And so let's use that. That means that we're going to say, okay, that means n needs to be greater than or equal to, at worst, this will be 4 times 0.5, this whole quantity squared, which means n needs to be 40,000. Okay. So that's conservative in the sense that if my real population proportion isn't 0.5, if it's further away from 0.5, especially really far, then my actual standard deviation of the population will be something less than 0.5, and that will make this number actually less than 40,000. But I'm guaranteed by doing a sample size of 40,000 to cover my basis, even in the worst case. And so that's what we're going to say. I would go out and recommend that you take a sample of size 40,000. And this is really key in how we do polling. This is actually a big piece in determining the sample size you need for a poll. And we actually have a name for this half the width of the interval of your confidence interval. So the half of the width of your confidence interval is referred to as your margin of error. So you may have seen headlines or seen this referred, especially around election time. Let's try an example with this. So how many Americans would you have to randomly poll to get a 95% confidence interval with a margin of error less than or equal to 3%? Choose the smallest number that's applicable. Again, go ahead and put this on pause and see what you can come up with. So the margin of error for a 95% confidence interval, well, that's going to be 2 times the standard error, which is 2 times the standard deviation of the population divided by square root of n. So if I want that to be less than or equal to 3%, I can go ahead and do all the same math I've been working through. Just did it in skipped a couple steps there to make it faster for us here. And then we're going to assume the worst case for the standard deviation, i.e. we're going to assume it's 0.5 because that will help us make sure we sample enough people in case the worst case is true. And so that's going to give me 2 times 0.5 or just 1 in the numerator. And that tells me that n has to be greater than or equal to 1111.11. I can't do 0.11 of a person, so we're just going to round up to the next integer. This is in fact, though, pretty remarkable if you think about it, and it was actually the topic of a headline from an election in the past. This was quite a while ago. This was 20 years ago, from 2004, but it was pointing out how amazing that actually a poll of just over 1,000 people can represent so many people with such a small percentage of margin of error. We'll point out that the 3% margin of error, the margin of error for 1,004 is slightly more than 3%. It's 3 point, something, because of our exact 3% would require a few more people. But even with that said, the 3% margin is definitely an understatement because opinions change. So in reality, a poll is a snapshot, not a forecast. And in reality, you may have pollsters say, you know what, then because of that, I want to give myself even more of a buffer, and let's try to go for like a 1.5% margin of error in theory. But even then, you would need about 4,000 people. So it's not a huge number as long as you're actually taking a random sample that is representative of the population. Let's do another one. I'm going to use a 68% confidence interval to estimate a population proportion. I want the total width of my interval to be no more than 2.5%. How large must my random sample be? Go ahead, put it on pause. All right, key things to remember here is for a 68% confidence interval, I would have my sample proportion plus or minus, but I'm not doing 2 standard errors, I'm only doing 1 standard error because we know that for a normal distribution, 68% of this area is within 1 standard deviation from the mean. So I'm going to have 1 times the standard error. And now I want the total width of the interval. So the width of this is going to be twice that. So it'll be 2 times the standard error. And I want that to be no more than 2.5%. So I want 0.025 is less than or equal to 2 times this. And again, let's assume our worst case for standard deviation, just because I don't have any other knowledge about what this is going to be. And now we're going to solve. So I'm going to get that n is greater than or equal to, I have 2 times 1/2 divided by 0.025 squared. And that's going to get me a random sample of size 1600. Last question. Suppose you are told a researcher is estimating a population proportion based on a random sample of size 10,000. Fill in the blank with what follows. With a chance of at least 95%, the estimate will be correct to within what margin of error? Go ahead, put it on pause, see what you can come up with. All right, for a 95% confidence interval, again, let's think of what our margin of error is. Normally we'd have our sample proportion plus or minus. For a 95%, I'm going to have 2 times the standard error. This is my margin of error. So this is going to be what I'm trying to see how small it is. So margin of error is, again, the worst case scenario is that this is 2 times 0.5 over square root of 10,000. So let's use that worst case scenario because we want a chance of at least 95%. And this tells me that my margin of error is 1 out of 100. And so I know this will be correct to at least within 0.01. It might be correct to even smaller amounts, especially if this is smaller. So again, we'll just say margin of error less than or equal to 0.01. So these are some examples of how we can use the theory that we've developed so far and our understanding of confidence intervals to help us design experiments before we've even gone out to collect a sample.